We spent the block day talking about how to determine the location of a value within a distribution. But when that really becomes important is when we talk about normal distributions. A normal distribution is a special type of distribution. In general, it looks like it is unimodal and symmetric, but it has some additional qualities that set it apart. In general, we describe a normal distribution using the mean and the standard deviation. So if you have a normal distribution, I should never hear the words median or IQR. We only use the mean and the standard deviation because they are essential parts of a normal distribution. Okay, the normal distribution is important to us because, one, it describes a lot of real data sets. There are many things that occur in the real world and in our lives that approximate a normal distribution. And in addition to that, it's a good approximation of chance outcomes. So if you have something that can occur randomly, the normal distribution gives you a good approximation of that. And finally, the normal distribution is where we get the ability to do our statistical inference. Without it, it's really hard for us to infer anything about a larger population or about cause and effect if our data does not follow a normal distribution. So let's talk about the shape of a normal distribution and some of the details. For example, batting averages. In 2009, the distribution of batting averages for Major League Baseball players was approximately normal. It had a mean of .261 and a standard deviation of .034. Okay, and we want to sketch this distribution. To sketch a normal distribution, you want to start with, in the middle, your mean. Because since it's symmetric, that means our mean and our median are always the same and always in the middle. So 261, and from there, that's going to be the peak of my curve. Then I'm going to make some evenly spaced tick marks and let each one of these be a standard deviation. So if I add a standard deviation of .034 to this, I get .295. I add another one, and I'm .329. And I add another one, and I'll get to .363. I always need 3 standard deviations above and 3 standard deviations below. So .227, I subtract another standard deviation, I get .193, and I subtract another one, and I get .159. Okay, I'm going to start at my mean, and I'm going to go to one direction and then the other. So I'm going to start at my mean, and I'm going to curve down. And about at 1 standard deviation is where my curve changes from concave down to what we call concave up. So my curve flips out the other way. And then it goes on and on and on past my 3rd standard deviation because it never actually ends. So it never touches the x-axis. And then I do the same thing on the other side. I go from concave down to concave up at 1 standard deviation, and I continue. And while they're not going to be perfect, they're close. Right? It is generally bell-shaped, which is why it's often called the bell curve. This right here, for all of you calculus people, just as a side note, it's called an inflection point. And in case you're interested, my calculus people, there isn't actually an equation that goes with this curve. It's 1 over the standard deviation times the square root of 2 pi times e raised to the negative of x minus the mean squared divided by 2 times the standard deviation squared. And this is e raised to all of this. So you do not have to know this for statistics, but in case you have had calculus and you're interested, that's the equation that describes this curve. Okay, so if I look, I actually below this have the dot plot for these players. And it asks what percentage of players had batting averages within 1 standard deviation of the mean. Well, my mean would be .261, so 0.25. This goes up by 0.01, so this would be 0.26, so 0.261 would be right about in here. And then if I went a standard deviation this way to 0.295, it would be right about here. So from here to here is 1 standard deviation. Okay, and if I go back the other way, I would be going to 0.227, so 0.2, 0.21, so right about here. And this is 1 standard deviation. So when it says within 1 standard deviation of the mean, it means either direction. So the words here within 1 standard deviation of the mean means to look in both directions. So it's asking how many points or what percentage of points are within this line to this line. And if you want, you can count them up and divide by all of the points, or you can just keep watching and find out with the rule that's next, which you may remember from Algebra 2. You may have learned this rule in Algebra 2, and it's called the 68, 99, 99.7 rule. The 68, 95, 99.7 rule, which is also called the empirical rule, is a way of estimating what percentage of points are within so many standard deviations. So if I look at my graph here, okay, this 1 standard deviation, so from 1 standard deviation below to 1 standard deviation above, 68% of the points. That's what the 68 in this rule is, that there are 68% of your data is from this to this. Okay, and maybe by now you've guessed that 95 is for 2 standard deviations. So if I went and looked for 2 standard deviations, that goes from 0.193, which would be about right here, to 0.329, which would be about right here. And about 95% of our data is within 2 standard deviations of our mean. And then the 99.7 rule goes from 0.159, which would be about right here, to 0.363, which would be about right here. And 99.7% of our data is within 3 standard deviations. Okay, notice it says, when does this apply? It only applies if your distribution is normal. Your distribution must be approximately normal for the 68, 95, 99.7 rule to apply. And something else to remember, this is an estimate. So not all distributions will be right on the money with this. There may be 66 here or 69 here, but it should be close to these 3 numbers. So you ask, what about if my distribution is not normal? There is something called Chebyshev's inequality, but you don't need to know anything about it. It is not an AP topic other than the fact that it is what works for non-normal data. So for skewed data or for data that may be symmetrical but not normal. So it works for non-normal data. That is all that you need to know. There is a little section about it in your book, though, if you're interested in learning some more. It has the equation. But all you need to know is that it works for non-normal data. Okay, so now, once we know that our data is normal, let's look at this dot plot of the number of points Michael Jordan scored at each of his 82 games in the 1986 to 1987 season. If I draw a density curve over this, I can see that it is unimodal and symmetric, so it has the possibility of being normal, and I can investigate it to see if it meets my 68, 95, 99.7 rule. So first thing I need to know is the mean and the standard deviation. So my mean is 37.1, so that would be about right in here, somewhere right around with these 2 points right here. 37 would be here, so we can call the mean this. If I add 9.9 to it, it would be right around in here. Add 9.9 to that, it would be right around in here. So this is 1 standard deviation, 2 standard deviations. If I add 9.9 again, 3 standard deviations would be off my chart. Okay, so if I go backwards, okay, minus 1 standard deviation would put me about here. If I said this, 37.1 minus 9.9. 2 standard deviations would put me right about here. 3 standard deviations would put me down here. So then if we calculate and count up the points, we know that there are 82 games, so that means there are 82 data points. So if I count up how many are from 1 standard deviation below to 1 standard deviation above, that's the points within 1 standard deviation, I find that I have 58 points out of 82, which is about 70.7%. Okay, if I then calculate from 2 standard deviations down to 2 standard deviations above, I find that I have 76 out of 82 points. So it's about a 92.7. And then if I go from 3 standard deviations down to 3 standard deviations above, this time I get all 82 out of 82, which is 100%. Okay, so while these are not right on the money, they are pretty close. I mean, ideally this one should be 68, so we're about 2 off. This one should be about 95, so again, we are approximately 2 off. And this one should be about 99.7, so we are close enough that we could qualify this as normal. Okay, it's also important that you don't say something is normal. We would say that this is approximately normal. Nothing is perfectly normal. Now would be a good time for you to stop and check your understanding. So stop the video, answer the questions, and then come back. So the first one, they want you to draw the normal curve. So your mean is 64.5. You would need to go up 3 standard deviations, down 3 standard deviations. 1 standard deviation this way would be 67. The next one would be 69.5, and the final one would be 72. If I go backwards, this one would be 62. This one would be 59.5, and this one would be 57. And I start at the bottom or the top. My inflection point from where I change curves is at 1 standard deviation. The peak is at the mean. Change curvature again, and there we go. Okay, number two, it wanted to know what percentage of the heights were greater than 67 inches. So here is 67, which is 1 standard deviation away from the mean. So I look this way. Okay, if I think about this as being symmetric, okay, because I know that the normal distribution is unimodal and symmetric, that means that 50% of my data has to be on this side and 50% of my data has to be on this side, which we also know because this is a density curve. The mean and median would be at the same spot, and the median is the 50% mark. So if from 1 standard deviation to 1 standard deviation is 68%, then that means from here to here must be 34. So to find this, I could say 50% or 0.5 minus 0.34, and I would end up with 0.16. That would be greater than, so 16% is greater than 67 inches. Number 3, and since I didn't use this one, we can use this one. For number 3, wants to know what percent of young women have heights between 62 and 72. So 62 is 1 standard deviation below, and 72 is 3 standard deviations above. So this is the area that I'm looking for. So I know that I could go from here to here, okay, is symmetric. So this is my mean. So this is 1 standard deviation this way, and this is 3 standard deviations this way. Okay, well from 1 to 1 here, okay, so if I took this, I know that within 3 standard deviations is 99.7%. So if I did this as a decimal, 0.997. And I know that I can divide that by 2 and I would get this area right here. And I already know from what we talked about earlier that from the mean to one standard deviation is 0.34 because it would be 68% divided by 2. So if I add these up, I should get approximately 84% of girls have heights between 62 inches and 72 inches. Let's look at this one other example. Suppose that a distribution of test scores is approximately normal, notice the approximately, and that the middle 95% of scores are between 72 and 84. So it wants to know what are the mean and standard deviation. So if I look at this, I know that if 95% of scores are between 72 and 84, that means that they are 2 standard deviations above and 2 standard deviations below my mean because it's approximately normal. So I can find my standard deviation by dividing this distance by how many standard deviations there are. So from 72 to 84 is a distance of 12. And if I divide that by 4, that means each one of these distances is 3. So my standard deviation must be 3. Then, to find the mean, if I know that the mean, if these two are 2 standard deviations below and 2 standard deviations above, then the mean would be in the middle. So if I say 72 plus 6, 3 and 3, that gives me 78, which would be the mean. Which means 1 standard deviation above 78 plus 3 would be 81. And 1 standard deviation below would be 75. So the next question says, can you calculate the percent of scores that are above 80? And while we can in the future, at the moment, no. Because the only knowledge we have right now is the empirical rule. So we have to go from standard deviation marks specifically, and 80 is not one of our standard deviation marks. So at the moment, no. We cannot. However, what we can do is work with something called the standard normal distribution, which we will learn about in just a second. First of all, let's talk about, though, the relationships between our z-scores, which we talked about on the block day, and standard deviations. I know that if I take a value and I turn it into a z-score, by subtracting the mean and then dividing by the standard deviation. So what happens if I take the mean and try and turn it into a z-score? If I take the mean and try and turn it into a z-score, I'm going to get 0 because 78 is the mean and 78 minus 78 is 0. So even when I divide by 3, it is still 0. So the z-score of the mean is always 0. The z-score of a standard deviation above, if I say 81 minus 78, that's going to give me 3. And so if I divide by 3, I'm going to get 1. Which means this would be a standard deviation, a z-score of 2. This is negative 1, and this is negative 2. The standard normal distribution is what happens when you take every value in your distribution and you turn it into a z-score. We know from talking about transforming data that when I subtract and divide, it leaves the shape the same, even though it changes the standard deviation and the mean. So by subtracting and dividing, I'm changing the mean here from 78 to 0, and I'm changing the distances between all of them to 1 standard deviation apiece. Okay, so that turns this into the standard normal distribution. The standard normal distribution is a normal distribution with a mean equal to 0 and a standard deviation equal to 1, and I get that by turning all of my data points into z-scores. Okay, now that I know about the standard normal distribution, I don't have to stick to my specific standard deviations in order to find percent above or below something. I can use z-scores and table A to help me find proportions of observations that are less than any given z-score, not just their specific ones. In order to be able to find the percentage that are less than any given z-score or greater than any given z-score or between any two z-scores, we want to use something called table A. Table A is in the back of your book. It is also given to you when you take the AP test, and I will give you a copy whenever you take any test in my class from here on out. But Table A looks something like this. And how we use Table A is that we go down and look for our z-score on the edge and across the top. So let's say that our z-score, this z-score right here, was negative 2.45. Okay, and I want to find this, the proportion of values that are under negative 2.45, okay, so that are further away from the standard deviation than negative 2.45. It's also the probability of getting a value that is this far or below away from the mean. Okay, in order to find this probability or that proportion, I come down this row until I find negative 2.4. And then I go and I'm going to look here. Okay, it's one of these values. Okay, my next digit is a 5, which means I'm going to go this way until I get to the 0.05 and look down this row. Where these two intersect, that's my probability. So if this z-score is negative 2.45, this probability is 0.0071. So there are less than 1% of values below negative 2.45. If I wanted to use Table A to find proportions that are greater than a given z-score, I use my knowledge of a density curve. I know that the area under this entire density curve is a 1. And if we use the same z-score, negative 2.45, if I know the entire area is 1, and I know that this area is 0.0071, then to find this area, I just say 1 minus 0.0071, and that would give me my area there. Okay, the other way I could figure this out is I could say that this is symmetric. Okay, we know that normal curves are symmetric. So the area that is greater than negative 2.45, okay, if it's symmetric, is going to be the same area that's less than 2.45. So if I'm looking for greater than, I can just take away my negative and go look for areas that are less than the positive. Just change the signs. And if it's a positive one, I can go look for the negative one. So notice all of these are negative. If I scroll down, okay, or go to the next page, I get positive z-scores. And so I do the same thing, 2.4, because if I find the greater than the negative, it's the same as less than the positive. 0, 1, 2, 3, 4, 5. So the area greater than negative 2.49 is the same as the area that is less than positive 2.49, and it's 1 minus 0.0071, and if you check this, that is 0.9929. So that is how we use Table A. Okay, you'll notice that at the bottom of your notes page it said, what should I always do? Okay, there are two things you should always do. One, draw the curve. I always want to see a sketch of the curve. Nothing detailed, nothing, okay. But I want to see that you know exactly what it is that you're finding. Two, if you need to find a z-score before you use the curve, you need to find your z-score. Show me your work. Whenever a z-score is required, you need to show me your work. So let's do some practicing with Table A. You can also do this on the calculator. I will show you how to do it on the calculator in class. On both the 84 and the Inspire, and I will post some videos of how to do it on the calculator on the website. So Find the proportion of observations from the standard normal curve that are less than 0.54. So if I draw my normal curve, which I always need to do, I know my mean is 0, so 0.54 would be right past the mean. So this is a z-score of 0.54, and I want less than that. So shade in your values. Then I'm going to go to table A. So less than 0.54. So 0.5 is right here. 0.5 is right here. And if I go over to 0.04, that is this one right here. So I get 0.7054. That is my proportion. If I want to find a proportion that are greater than negative 112, so mean is here, that would be down here, and I want to find the ones that are greater. So I draw my picture, I go to table A, and when I go to table A, I can do one of two things. I can find what's less than negative 1.12 and subtract from 1. Or since I'm already on the page with the positives, let's find what is less than positive 1.12. Because since they are symmetric, it's going to be the same. So 1.1 would be here. This is 0.00, 0.01, 0.02. So my answer would be 0.8686. And notice right now they're giving me my z-scores, because they're telling me that this is a standard normal distribution, so that means that this is a z-score. Find the proportion from the standard normal distribution that are greater than 3.89. So again, I can find what's less than 3.89 and subtract. Okay, so we'll do it that way this time. Negative 3.89, and you know what? 3.89 is not on our table. So we will have to use the calculator. So some of these, which is a good lesson, some of these your table only goes up so high. So on ones like this, where they're not on the table, you have to use your calculator. You will not ever see any where you cannot use table A. Okay, I will always give you ones where table A is an option. The answer for this, and you can go back and try it whenever we talk about the ones, and we will talk about this one in class when I talk about how to use the calculator. 4 zeros and a 5. So, find the proportions of observations from the standard normal distribution that are between 0.49 and 1.82. Okay, this one is a little different because I'm finding between two. So, I have we'll say that 0 is in the middle here. And now this doesn't exactly look like the middle, so let's move it over. 0 is my mean. 0.49 would be right beside it, and 1.82 would be a little bit further this way, and I want this. Okay, where this is 0.49, and this is 1.82. Okay, if I think about this distance right here is really this minus this. So if I find the area under 0.49 and I find the area from 1.82 and I subtract them, that's going to give me this area here in between the two. So I go use my table A. Okay, I'm looking for less than, so I can say 0.4 would be right here, and if I go over 0.49 would be 6879, and then I find 1.82 is 0.9656. So when I subtract those, 0.9656 minus 0.6879, I end up with an area of 0.2777. Okay. Then I find what proportion of observations from the normal distribution are within the 1.5 standard deviations of the mean. Okay, well, since I'm wanting to know standard deviations, that's basically a z-score. How far away am I in terms of standard deviation? So I'm wanting to know what's from negative 1.5 to 1.5. Okay, so I need to subtract these right here. So When I do that, I go and I use table A to find the areas here, and I find that this area right here is 0.0668, and I find that this big area right here from 1.5 down is 0.9332. I subtract those, and I get 0.8664. There is another way to use the standard normal curve. This one is to go backwards. Here we know that a test score is approximately normal and Joe scores in the 85th percentile. We know from our definition of percentiles that that means he scored higher than 85% of people. So that means that wherever he is on the normal distribution, whatever this value is, the proportion of people beneath it is 0.85. Okay, I can use table A to also go backwards from an area and find a z-score. And then, okay, and that will tell me how many standard deviations above the mean. And I know it's above the mean because the mean would be the 50th percentile and he's above that. So I go to my table A and I'm going to look for an area that is as close to 0.85 as possible. So I see 0.8508 and 0.8485. This one's 15 thousandths of a way, or 10 thousandths of a way, and this one is only 8 10,000ths away, so 0.8505 would be as close to the 85th percentile as I could get. So then I scroll over here and I find my z-score for this. 1.0, and then I look up here and see that the 100th digit is a 4. So that means that his z-score was 1.04, and he scored that many standard deviations above the mean. Okay, so for the very last thing in the video, there's a check your understanding. So go ahead and pause the video for a second, answer these 5 questions, and then check your answers. And we get 0.9177, 0.9842, 0.6772, negative 0.84, and 0.13. And be on the lookout for videos, for calculator videos, because they will help you. You don't have to use the calculator. Table A is just as good. But there are some things on the calculator here that you can use instead of table A. So be on the lookout for some calculators.